morning. Today we're going to look at the design of a pitch or roll damper. Now this is a typical block diagram of a pitch or roll damper, and the main things that are important is we've got a little actuator here and we've got a 1/s term over here. This is usually related to pitch angle and pitch rate, or roll angle and roll rate. And we have a derivative feedback controller in here, KD. And the job is to design KP and KD so as we can achieve a certain damping ratio, let's say 0.5, and a natural frequency of say 3 radians per second. So this is our design specification, and we've got to find KP and KD, and we're going to use it to do the solution. We are going to use the angle and magnitude criteria, and for that we're going to have a little plot in our real imaginary plane. Now the first thing is we can't actually solve the problem as it stands here because it's got 2 feedback control loops in. So we've repositioned our second feedback control loop, so we've actually got this. So we redesign the control system. So as we're adding in a 0 at minus K2, we have a proportional gain K1. Now these K1 and K2s are not the same as these, and there's a quick way to go between the two. The KD is providing the derivative control, which is the S term, so therefore KD is actually K1. So this one will end up as K1. And the proportional control, this is the proportional part here, this will end up as K1 times K2. So our design now is in this format here. Now looking at this, we've got a pole at 4, so we got minus 4, so you can put a pole there. We've got a pole at minus 1, so we've got a pole here, and we've also got a pole at the origin. The 0, we don't know where it is, but somewhere along here will be a 0 at minus K2. So minus K1. Making a mistake here. But we don't know where that is yet. That's an unknown quantity, which we're trying to find now. It was wrong. It was K2. Right, so what we're going to do next is take these parameters here, that's the zeta and the omega n, and we're going to stick them into our second order system equation, s squared plus 2 zeta omega n s plus omega n squared equals 0. And from this we can find out the location in the complex plane of the desired second order system response. So s squared is s squared. 2 zeta omega n will be 3 s, and 3 3's 9. Now we can solve this using the famous formula, minus b plus or minus square root of b squared minus 4ac, and we'll get a solution as s is minus 1.5 plus or minus j, remember j stands for Jones, and it's 2.6. So these parameters here that give us this equation, which then go to here, solve it, and then from this then we get a point at minus 1.5 plus 2.6j in our Argand diagram, which is here. So what we can do now is to use the angle criteria to locate K2. So this is relatively straightforward. Take a ruler, which I've got made specially for this experiment, and we draw lines in now from the poles to the poles, like this. And we know there's also going to be a 0 somewhere here, but we don't know where that one is at the moment. So to locate this point, we can use the angle criteria. So we've got the angle criteria, which states now that the sum of the 0 angles minus the sum of the pole angles adds up to exactly 180 degrees. So we can now take our protractor. I've not got one with me today, but we can measure this angle here and call that beta 1. Measure this angle here, call it beta 2, and measure this angle here and call it beta 3. So we'd have to measure those with a protractor, and we'd have this angle here, alpha 1, but we don't know what alpha 1 is. So we now put these parameters into this equation. So we get alpha 1 minus beta 1 plus beta 2 plus beta 3 is equal to minus 180 degrees. And in this equation, we know everything but for alpha 1. So had I got solving this, and alpha 1 comes out as 87 degrees. Now what we do now is we draw a line parallel to these, like this. So as this line parallel to that one, and then what we do is we measure this way 87 degrees. Where it cuts then here, this distance from here to there is minus K2. Or for our purposes we consider it to be plus K2 if we measure that direction. So that then gives us the part of the solution now to K2. So that's the first stage. The second stage is to work out what the gain K1 is. Now to do this, we'll need to make use of the magnitude criteria. And we'll also need to use our ruler to measure now the distances off this diagram here. So we could measure from there to there and call that, say, M1. Measure from there to there, call that M2. Measure from there to there, call that M3, and then from there to there we'll call M1 hat. So we've labelled the pole distances M's and the 0 distance M1 hat. The magnitude criteria now tells us that the forward loop gain on here, which is 4, so 4 times K1, because you've got a K1 and the 4, and that's multiplied by the product of the 0 distances, which in this case will be M1 hat, divided by the product of the pole distances. So it's going to be M1 times M2 times M3. And that's equal to 1. So in this equation, we can solve for K1. And if we do that, we find out that K1 comes out as 5.52. So now we've got a solution of K1 as 5.52 and K2, and if we do K2, it comes out as K2 comes out as 1.65, so that's actually the point minus 1.65. That then defines K1 and K2 for us, and so K1 is in here, so this is going to be 5.52, and in here it'll be K1 times K2, which is 5.5 times 1.65. And then that gives us our final solution to the pitch or roll damper design.